Good morning. With this video we would like to get the equation of the finite element method, Galerkin finite element method, using the three-dimensional, two-dimensional and one-dimensional head transfer equation. First of all, the finite element procedure using the Galerkin method can be described by the following steps. Step 1. The step 1, you have to divide the domain V into E finite elements of P nodes each. The step 2, you have to assume a suitable form of variation of T in each finite element and express the function T, because it's a head transfer problem, in element E as Te equal n multiplied the vector T of the element. That means T superscript E x, y, zeta and t is equal to n of function of multiplied by the vector t. Vector t with superscript e is the value of the temperature at nodes. Then we have a step 3. In the Galerkin method, the integral of the weighted residue over the domain of the element is set equal to 0 by taking the weights same as interpolation function n I. Step 4. After including boundary conditions and performing calculation, we can assemble the overall equations. The overall equations in this case is K3, that is a matrix. First derivative respect to time of t plus the matrix key, we will see how to get it, multiplied by t equal to p. We have to note to observe that here we have now the superscript e. That means that is this equation refers to the overall domain. Then we have a final step, step 5, in which this equation have to be solved after incorporating initial condition and boundary condition specified over S1. First of all, we have to start by writing the governing equation. The governing equation is kx with respect to x plus ky the y plus derivative of respect to zeta of k zeta d su the zeta, and this we have to add this term and this term equal to 0. Now we have the governing equation. Then we have to choose, we have to choose the the interpolation function t of function of x, y, zeta and t is equal to n function of x, y and zeta but not t multiplied by the vector. This is the interpolation function, and this is the vector of the value of the temperature at each node in the element. We have to underline in the element. We are considering only one element now. If we use the Galerkin method, using the Galerkin method, the governing equation, the integral over the domain, that is v of the element, multiplied by each interpolation function ni, must be set equal to 0, and so we obtain a set of equation. So we can write v e of the kx the element the x plus 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 derivative of q respect to time minus rho c, that the superscript e, multiplied by ni in the interpolation function. The domain is v, so we have to put the v and set this set of equation equal to 0. Obviously e go from 1 to p. P is the number of nodes in the element, and this is related to the choice of the interpolation function, linear, quadratic, cubic, etc., etc. After that, we can integrate these terms. We can first of all divide this integral in subintegral, but if we consider only this part underlined, we can integrate it by parts in 3 dimensions. Integrating by parts in 3 dimension, we can write VE plus this multiplied by Ni dv, and this is equal, integrating by parts, to minus plus the boundary condition that we can write as S, that is the external surface of the element, and I kx ds. Now we have to specify what is ix, iy, and zeta. Is simply the direction cosine of the outward normal to the surface in a point in respect to x, y, and zeta. So we can write minus this term that we call 1 plus this term that we call 2 and we have to add these two terms of the relative to the governing equation, and I multiplied by Q dotted rho C dt element, okay, equal to 0 with I from 1 to P. Now we have to consider the boundary condition. Boundary conditions are on S1, then, and this is the first boundary condition, then kx plus ky, this is an error, we don't have the plus but is a multiplication, plus k zeta dt the zeta e zeta equal to minus q0 on S2 after the final boundary condition, and this is relative the convective term, this is equal to minus h t minus t infinite on S3 for t bigger than 0. Now consider the second integral and divide the domain in S1, S2, S3. The second integral is, we can rewrite the integral ni kx plus etc etc and k zeta so you can recognize using the boundary condition that is equal to, in this case, S2 element plus S3 of the element, and this term is equal to this equation and also to this equation. So if we divide S2 ni kx plus the S2 plus S3, that is the integral domain ni, and this is the same, kx plus kz that's 3. We can see that this term is equal to minus q0. So this term on S2 is minus q0. This term is equal to minus h t e minus t infinite. So we can rewrite the second integral. And if we rewrite the second integral, we can write as 2 element minus ni q0 the S2 minus integral on S3 of the element e h t of element minus t infinite the S3. Now we have to consider what we have said at the beginning, that t function of x, y, z and t is equal to the sum of p of the node j1 beginning to 1 and j tj. So obviously the x is equal to of the sum j to p and j tj, that is equal to the sum is you can guess, because we don't derive the t, because t is a constant, tj is a constant for each node. The only value that vary is nj, that is function of x, y, and z. Similarly, we can write the y and the t, the z. So the overall integral so we can remind which integral is. So means that this integral 1, integral 1 becomes minus on the domain vi just a moment. Kx the and I the and the sum p j equal to 1 the nj x tj plus ky the ni the y sum j equal to 1 and this is equal to the sum of integral plus ky term and I the theta j zeta tj. We have simplified a lot. So the matrix K1, the matrix term EJ K of the matrix K1 of the element E is equal to sorry. Okay, now we have the first matrix. As concern the second matrix, k to I, it derives from the integral we have seen before, S3 of element, H T of element, that is equal to minus S3 of element E, H T E, we have forgot before this, Ni dash 3 plus H Ni dash 3. So if we focalize the attention, yes, this term is not is a known term, and we know him P3. So if we focalize on this term the attention, we will get S3 H T E Ni dash 3 is equal, considering what we have said before about the temperature distribution and the interpolation function, becomes H P G equal J equal to 1 of Nj Tj multiplied Ni dash 3. So after some algebra, after some algebra, we can say that K2 EJ the EJ term of the matrix K2 is equal to 3E H A E N J dash 3. We are almost done. As concerns K3 of the element E, we have to consider this integral we have seen at the beginning. Ni is equal to we divide the integral by the summing property of the integral minus ni rho c e over the t, the v. We focalize the attention on this integral. This integral is called P1, but we focalize the attention over this integral here. We know that t is equal to sum j1 p, as we say before, and j tj. So the t on the t is equal sum and j p but nj is function x, y, and zeta, not t. The only terms that is function of t in unsteady state problem is tj. So the t on the t is equal to the sum p j1 and j, the tj on the t. And we can write in another notation as the sum and j tj dotted. Therefore, if we consider the integral before with ve ni rho c, sum of n j t dotted j dv if we expand the sum as before, we obtain minus rho c ni n1 t1 point of element e dv plus, anzi minus c ni n2 t2 e dotted dv plus tac 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 until ve rho c ni n p t p e dv, that is equal to minus sum j after p rho c Tj. So K3EJ, that is another matrix, is equal to this quantity we are almost done. We can write, collecting all what we have said before, minus k1 of element E, t of element vector t, minus k2 of element E, the other matrix we have obtained, t vector E, minus k3, the last matrix we have obtained of element E, t dotted E is equal to P. But P is composed by P1 minus P2 plus P3, in which P1 is equal to the term we have obtained before, and I dotted the V. P2 is equal to S2 Q0 and I dash 2. P3 is equal integral on S3 H T infinite and I dash 3. After all of that, we can write, we can rearrange the equation, and if we sum K1 matrix K1 plus K2 uguale of the element, we can write K1 ANSI, we can write K of element T plus K3 of element T dotted E minus P equal to 0, and this is the finite element set of equation using Galerkin mode, Galerkin approach, that then this is the most general. Now we have to specialize, choosing, for example, the interpolation function, choosing the domain, etc. We can specialize this equation. We have to find the matrix the two matrix using different approach. If we consider one-dimensional problem, we will have an equation, a set of equation. If we consider a two-dimensional problem, we will have to use another kind of finite element, so we will have a different, but the overall equation, set of equation, remain the same.